Hello everyone! In this lecture, we're going to talk about generative modeling. So far, we've seen that neural networks can be used to predict an output, which can be continuous or discrete, where the inputs can have different forms: tabular data, images, text, and so on. Our aim here is quite different, since we want to study the distribution of the data, which contain no labels. One ultimate goal may be to produce data that are distributed as an original sample we have at our disposal. We will start by giving circumstances in which we want to study the distribution of the data or to generate new data. We will see classical statistical methods that aim at estimating the density of the data. The density can then be used to produce data. This will be the subject of the part No Latent Variables. A latent variable is an extra variable that is not observed in the data set, but that could really help to understand the mechanism that produces data. The third part, to be seen in the next lecture, will be dedicated to methods that use latent variables such as the EM algorithm, variational autoencoders, or generative adversarial networks. So let's start our journey in the generative modeling world. Remember that in a supervised setting, we assume to be given a data set composed of pair xi, yi, where xi is the input and yi is the associated output. You can divide the method used to solve supervised problems into two sets. First, discriminative models that aim to estimate the conditional distribution of y given x. These methods are the most common in statistics: linear regression, logistic regression, generalized linear models, neural networks as ANN, CNN, RNN, and also non-parametric statistical methods such as decision trees, boosting, random forest, and other methods such as kernels, nearest neighbors, and many more. Estimating the conditional distribution of y given x can be directly used to build a prediction. This is why these methods are the most common in machine learning. The second type of models are the generative models that aim at estimating the joint distribution of x, y. Among these models, you can find the naive-Bayes approach together with the linear and quadratic discriminant analysis. These two classes of models are really different. In the first one, you estimate the conditional distribution of y given x, which can be used in order to predict. In the second one, you estimate a more complex distribution, the joint distribution of x, y. Estimating the joint distribution is a more complicated problem because you can retrieve the conditional distribution based on the joint distribution, but the opposite is not true. You would need to have the distribution of x and y given x to do so. So quite logically, if you want to predict, you will likely use discriminative models because your aim is just to build a prediction. But if you want to generate data, you need the full joint distribution of x, y, and then you need to use generative models. However, generative models make stronger assumptions on the data than discriminative models. For example, in the naive-Bayes model, you assume that the input variables are independent, conditional on the output. In the discriminative models, you do not have any assumption on the distribution of x, since you only model y given x. In this lecture, since we want to generate data, we are interested in the second class of models, which are the generative models. So this was for the supervised setting, but we will consider more frequently in this session the unsupervised setting. Recall that in an unsupervised setting, we assume to be given a data set Dn composed of x1, x2 until xn, where xi is the ith observation. There are no labels in this framework. There exist many different goals in unsupervised learning. You can use descriptive analysis in order to detect structure, correlations in the dataset using descriptive graphical tools or using more involved methods such as PCA. You can cluster your individuals to create homogeneous groups of observations, usually spending a large amount of time to properly define homogeneous. The last two goals are our major concerns in this session. You can estimate the distribution of observations to detect suspect data or suspect behavior, detect changes in the data set if the data are collected through time. Indeed, if you estimate the distribution of observations, it may help you to detect data that are far from the average that you can investigate afterwards. These data, often called outliers, may be legitimate or may result from measurement errors, data collection error, which need to be corrected. You can also generate new data. This aim is closely related to the previous one of estimating the data distribution. Indeed, if you have access to an estimation of the distribution of observations, then you can use this estimation to generate data. However, you can also find methods to generate new data without having to estimate the distribution of observation first, and this is permitted, for example, by the use of neural networks as variational autoencoders or generative adversarial networks. So keep in mind that neural networks allow us to generate new data without having to estimate the data density first.